All right, let's jump right into this explainer and tackle what I like to call the terrifying blank page problem. You know the feeling. You're assigned to a massive, multi-million dollar offshore project. You sit down, pull out a fresh sheet of paper, and you're told to design the entire electrical system from absolute scratch. It's a daunting moment, right? But today, we're going to break down exactly how you conquer that blank page by mastering the estimation of the plant's electrical load. So, the obvious question is, where do you actually start? Because here's the reality. You literally cannot size a single cable, you can't pick a generator, and you definitely can't specify a transformer until you answer one fundamental question. How much power does this massive steel island actually need to just survive and operate? I mean, it sounds simple, but calculating that exact foundational electrical load is basically the bedrock of your entire engineering design. And getting this load calculation right the first time, it's absolutely crucial. The stakes here are incredibly high. If you underestimate the load, well, you're facing catastrophic power trips on day one. The whole platform goes dark, production grinds to a halt, and safety is severely compromised. No one wants that. But on the flip side, if you play it too safe and wildly overestimate the load, you end up wasting millions of dollars on unnecessarily massive capital equipment. You've got these huge, oversized generators just sitting there, burning budget. So yeah, it's a very delicate balancing act. Section 1. Why load estimation comes first. Think of electrical load estimation exactly like building a house. Before you choose the size of your water pipes, you absolutely need to know how many taps, showers, and toilets will be running simultaneously. In oil and gas, we do this exact same thing using a preliminary single-line diagram. Every single load has to be plotted out, but instead of taps and showers, we're looking at massive motors, lighting setups, and HVAC systems. We have to map out what runs at the exact same time so we know our power generation can actually handle the maximum flow. Section 2. 2 dimensions of every load. Now, every single one of those loads has to be categorized in 2 dimensions. The first dimension is criticality. Basically, what happens if this machine loses power? We rigorously split this into a 3-way setup based on safety and production. First up, we've got vital loads. We're talking fire and gas systems, ESDs or emergency shutdowns, and emergency lighting. These absolutely cannot fail, ever. Next, we have essential loads, things like process pumps, main lighting, and HVAC. If these go down, you lose your manufactured product and production stops. And finally, non-essential loads. This is your workshop equipment, non-critical ventilation, or the galley. Look, losing the coffee machine is definitely annoying, but it's not going to blow up the platform or stop the oil flowing. Okay, moving on to the second dimension, duty category. This asks a simple question. How often does the equipment actually run? First, we have continuous. Just like it sounds, this is equipment running 24/7. Then we have intermittent, which means it runs occasionally, specifically less than 30 minutes an hour, kind of like a sump pump. And finally, standby. This means the equipment is essentially asleep. It's a backup unit that's not normally running at all unless the primary unit happens to fail. Section 3. The electrical load schedule. Once we've compiled all of that categorized equipment into one massive master document, we introduce what's called the diversity factor. Think about it. If we just added up the raw nameplate rating of every single motor and light bulb out there, our calculated load would be astronomically high. There's no way. So the diversity factor is this brilliant mathematical multiplier that gives us a realistic simultaneous power draw. It acknowledges the simple reality that not every industrial machine runs at 100% capacity at the exact same time. In the conceptual design phase, we anchor these calculations with standard multipliers based directly on those duty categories we just talked about. For continuous loads, we multiply the power rating by 1.0 because we assume it's pulling full power all the time. For intermittent loads, we multiply by 0.5. We're basically saying it only contributes half its weight to the overall simultaneous load. And for standby equipment, we use a multiplier of just 0.1, meaning we assume it's sound asleep about 90% of the time. Section 4. Sizing generation capacity. So, by applying those multipliers across all the switchboards, the math actually becomes highly structured. Step 1. We methodically calculate the normal running load, known as the TPRL. Step 2. We calculate the absolute peak draw, the TPPL, to account for extreme or abnormal conditions. And then Step 3, we take those concrete, mathematically backed figures to confidently size our main gas turbine generators. We finally know our exact target. But hold on, we aren't quite done yet. As engineers, we always have to ask the what-if questions. Like, what happens if a generator unexpectedly trips? That brings us to the famous N-1 philosophy.
This is an absolutely crucial safety margin in the oil industry. It simply ensures that if you have N number of generators and one suddenly fails or has to be taken offline for maintenance, the remaining N-1 generators can still step up and supply the total plant load. No cascading blackouts, no shutting down production. It keeps the whole show running.
To visualize a perfect N-1 design, we ideally want those remaining online generators to run at around 75% capacity. That is the absolute sweet spot right there. It means they're running efficiently, but more importantly, it leaves a 25% reserve capacity. This buffer is critical because it ensures the generator stays safely below that dangerous 125% overload trip threshold if another machine suddenly kicks on. It's all about building in bulletproof resilience.
So as we wrap up this explainer, I want to leave you with an empowering thought. Whether you're designing an offshore platform, mapping out a giant data center, or literally just figuring out the plumbing for a new house, how might you apply this structured load-first thinking to completely de-risk the blank page of your next complex project? Because once you truly know your foundational load, the rest of the design just naturally falls right into place. Thanks for exploring this with me.